of continuity, embarshing, isn't it? And one-to-one, and so on and so forth. We saw last week that topological manifolds are very important in study of shapes, especially, and that's why it's very relevant, also very connected to algebraic geometry, and so on and so forth. And we saw how it also relates to general math, general function theory, and how we were able to use it to transform one topological structure onto another in form of replication, in form of representative, as a representative picture. We gave some example. We shall continue to give examples. I have one here of a map x from u to r square, so that f of mn is minus m and n. We have a map f which takes some 3v, okay, v is some space, two-dimensional, unit length, a square, where mn is transposed to actually minus m. So this map is one of the example of the transition map, actually, which now transform a figure from its original location or its original position to an inverse of it, or to a negative of it, whatever that negative means, or that inverse in times, or maybe in terms of translation, change in direction. If I talk of vector space, maybe from facing east to facing west, or from facing north to facing south, or even inversion, maybe the head comes down, tails goes off, and so on and so forth. You can have so many maps like this. Supposing we have something like this as a two-dimensional space. I know what it means in two-dimensional place. Space we have this is R, this is two. Already this is two-dimension. So you have a figure, a point, a figure from here, maybe, to another, maybe from one-dimensional space to, this is also a n-dimensional space. You map it to another one from two-dimensional, so you are mapping from V here to R square. Okay. So if you have a figure, this may look like this. Maybe when you have a figure, say L. Okay. It may look here in this dimension, this space. It will look like this. Maybe something like this. In my case, it looks like symbiotic. So this space comes here. It's not here. Because you have two different spaces. This is when it is in B. This is when it is in the other space, and so on and so forth. And you may also think of this map as maybe even magnification. Maybe a map, you may have a map which takes some points M to maybe 2M. 2M, something like this. This looks like something double, maybe it doubles the size and so on and so forth. And so on and so forth. The map may also take S and T, maybe they are square root. S. Something like these are all maps which are possible. And what we call this, we are now transforming these shapes from what they are to something else, but within the real world situation. These are what we call chart maps. We We call them chart maps actually. So what we do, what we say in that case is that we say this is the chart of this. This figure is the chart of this figure. This figure is the chart of this figure, and so on and so forth. Depending on how you want it. Just like we are taking video here. We may wish to magnify our video, we may wish to make it smaller, and so on and so forth. So we always have these charts. And what are charts? They are just replica of the real world objects. Yes, the real universe is actual universe. Because it's not always possible to have the objects themselves. Sometimes it may suffice to have the replica on some, just like having a photo of a very big mountain on a piece of paper. You can imagine how big maybe the Zuma mountain is, and when you have this photo and it's simple A4, maybe some portion of A4, you have the whole Zuma rock there. So we say we have a chart of it. It's like we have shrink the Zuma rock into so small portion that you can even represent it on a simple one-dimensional space. The Zuma rock itself is not one-dimensional, it's a two-dimensional figure. But you can reduce it to just one-dimensional. So that's what chart maps are, and what we saw last week, that the combination of these charts is what we call atlas. So you may think of atlas then of the real world as a very big book containing charts of different positions, different towns, different states, different countries on the real world, yes. So we now graduate to what we call chart transition maps. Chart transition maps. So that's the next one we'll look at. Look at chart transition map. What a problem with this. Particularly this. Now, what we mean by chart transition map is sometimes you may have a situation where you have more than one map of the same object, of course on different n-dimensional topologies. Then what happens is that you may wish to know how do you translate one chart with respect to the other, or how do you glue the two charts together. For example, maybe you have a situation where in a space you have two spaces. Maybe space M, and inside M you have a smaller space, maybe S. So the bigger one is M, the smaller one is S. Then you will discover that this region lies in the intersection, S intersection. The two spaces are intersecting here. Is it clear? Now points in this intersection may be represented by different maps. For example, you may have a map S here, which translates these points on some n-dimensional space. Clear? And maybe it replicates maybe these portions like this. You may also replicate the same point on another n-dimensional space, maybe like this. Okay. Let's call this T. Okay. It's the same portion, but it's being replicated by two different maps. Map S is showing it like this. Map T is showing it somewhere like this. So sometimes you may wish to see how do you now glue this. Or you may have a situation where you have one is bigger like this. How do you glue this onto this? Because it's the same portion you are actually marking. It's the same because it's intersection. Of course, S is acting on this, M is T is also another different map, but on the same, they are map of the same portions on the real world. So in Atlas, you may see them somewhat like this, the other one is on that side. So you may wish to now glue them together. So you have now, if you look at this point, what is the vector this point generates? You want to look at it as a vector now. You find out that if you pick a point here and you want to know the implication of these two maps on this point, then you will say, for example, T after S inverse applied on a point here. Because if you look at this, S inverse then will go in the anti-clockwise, isn't it? And it will now combine with T, and it will produce some point here. This is okay, it's on here. So this is what? T after S inverse. So depending on points, now maybe this is P1 or P1, T after S inverse, or P2, T after S inverse, or P2, depending on your points. So you can now generate the transition. This will now transit you. This will now transit you from T, from S to what? T. It will give you the cumulative effect of the two maps on the same point. Instead of taking the map T separately, S separately, you are now trying to combine the two maps. Since they are all marking the same point, and this is what you call chart transition. You are now gluing this figure with this, so that you will have one figure representing the two maps, because they are all representing the same place after all, the same portion of the axis. Now if you look at this, you have so you, just like you have this, so this will look like you are now saying that you are trying to compute T after S inverse of this point. So take S inverse of the point. You are going to have an image, isn't it? Now, on this image, apply T. T is a map. So whatever you get is like this. Looks like composition, isn't it? Somewhat like composition, like you are doing some composition of mapping. Yes. But we don't want to call it composition of mapping here because we just want to say that it is simply taking T map on the image of S. Is it clear? So we are now saying that we are transiting, not composing. In other words, we are not putting the two maps together, but we are transiting from one to the other. Yes, so that at the end we are going to get a single map. So if you see this vector now, for example, if I may draw this vector, I will have a point here, and this I call S intersection M. Then on this point, I have one here, I mean here go. This is what we call S-O. Maybe I have S here. Maybe I have what? T. So maybe you wish to know what this point is. Okay? This is T. This is S. This is T. We wish to know this. Okay? This is simply what?
T after.
T after.
S in.
S inverse. Yes. T after S inverse. Yes. So that's what you get here as the point is. So you now have this is because you are now marking them on the same point. So at this point you have what S of S intersection M, isn't it? And at this point you have what? T of, isn't it? S intersection. So you can now see that you started from here, but you transited to here. So that's what we call chart transition maps. Somewhat similar, somewhat synonymous or similar concepts is what you look at sometime when you talk of functors in function theory. Yes, where you have various arrangements of functions different or flying in the same different directions to have an equilibrium sort of function at a point, so that at the end you have so this looks like a transition, like movement. You are moving from one to another, and this is very important in manifold theory, and I think in differential calculus, if you look at, you may wish, because you may wish to ask questions now, is this mapping differentiable? We know it's, but these mappings are all continuous. Both T and S are both continuous maps. Okay. On what? Of course, there are maps on S intersection, the region, and they're also one-to-one. So that means the hypothesis siblings are one-to-one, and they're invertible. Their inverse is also continuous. It's just like you require also in manifolds. You require continuity of the maps and continuity of the inverse maps. But differentiability is something else, because you have to look at other factors to establish that. But up to continuity, this is true. You can always transit from one to another. And somewhat like concatenation also, which you also look at concatenation of maps, which also try to put together different maps to give you one idea about what they do to a point, or to an object, or to a space. So we look at this, we call this chart transition maps. In diagrammatic sense, it will look like something like that, although I gave a diagram. It will look like something like this. Suppose you have two spaces like this, two manifold, what may look, this S may look like this, while the other may look somewhat imagine you have something like this. 1/2, maybe this is your S, this is your M. So the portions, so you will try to, what you are trying to do is to try to glue this onto this one gives you a part of it, this one gives you the other part. What you are trying to do is to bring this to glue them together so that you have one shape, and that's what the TRS embassy is doing. Okay? On points of this. On different, maybe these are different papers on the atlas. The page 84 is showing the map of this like this. Page 85 is showing, so we want to see how to glue them together to have one shape of the same. You can imagine this as maybe sending 2 aircrafts, 2 surveillance craft to take a picture of a particular facility. The other one coming from east will take some picture showing this side. The other one from west will come and show this picture of this building from this side. And each one will post the picture on its chart. So you have 2 charts of the same building, isn't it? This one is showing you the right hand side, this one is showing the, you may wish to have a sense of gluing them together to have one shape of this building. So what you do the chart transition. Okay, good. Now, in manifold theory, it is desirable actually to define properties using continuity. Like I said, what we are leveraging on is that our maps are continuous. Because if our maps are not continuous, we have problems. Because it means these are open sets, for example. They are not going to be mapped onto open sets. They are going to be mapped onto something else. And that will generate a problem. And by continuity, it means also that each point on this has a replica on the other side, and the vice versa. That we can always translate a point on the image, okay, on the image back to its corresponding object position on the object. So with this, we were sure that our maps are actual replica of the object. What happens if a point, the map S here, is taking a point P1 to something else, maybe S of T or S of P inverse, instead of S of P, is taking the inverse. You may have problem or something like that, or of entirely different object, maybe S of L or something. When you are looking for P, you are getting L. It's like you are trying to take a picture of a human being and you see a God picture appearing, isn't it? So that means you are not continuing. Or you are trying to get a photo of this building which looks like triangular, and they give you a picture of something round. Is it clear? It may be not, it may not be. Or you want a picture of a school, and they gave you a picture of a house, a single house. So you can see that there's no continuity there, because points in this school are not mapped one-to-one to points in a single house, because you have different portions in this school which are not covered, because this is much bigger than a house, isn't it? It does not even look like a house, so on and so forth. So you can imagine if you are trying to get information, you'll be getting wrong information. Yes, you are liable to get wrong information if you are not. So a liberation on this. So we are saying in the real world, if we ensure continuity and embassy is also continuous, so on, we can use that to now generate replica of different objects. So we call such objects the charts. We say we are getting the charts of those objects. And example, I think, okay. The disadvantage of this assumption is that because we are assuming that all maps are continuous, and we are assuming that we can liberate on assumption of maybe the position.
I see that the other one will stay at a certain position, allowing the first one to land the first for the other one came down, and that is the standard. Is it also the application of this map chart maps?
Somewhat. I think to some extent, but it's more like the also it's of course it is, because we are choosing our trajectory. That means it's one of the things we say that once we can determine our trajectory, then these concepts will work, because we use the vector calculus and as algebraic formalities of vector, and we can easily compute the positions of objects. If you are saying that deliberately allowing one to, it's like you are determining now the trajectory of the two planets. And once you do that, you can always conclude on when they will land, where they will land. Yes. So it's one of the assumptions we make. We always assume our x. Because if you don't have your trajectory, then you cannot compute the transition. You have to know the trajectory first. So that's one of the disadvantages of this manifold philosophy, that we always assume a given trajectory. But who tells you that every time it has to be that trajectory? What happens if somebody or somewhere or something decides otherwise? Yes. Okay. So, like for example, this is your space. Maybe this is my space, like you said. Maybe your aeroplane. You always assume that your aeroplane should start from point A here, maybe B, C. Your aeroplane wants to go from A to C. You will always assume that this is the chart with the path between it. Okay, you will always assume that you should take the diagonal, because it's faster, it's shorter. Yeah, so maybe this is your x, path x. This is A. This is x of what? A. And you say it's what? If you apply mod x on A, and if you apply mod x on A, you will land at what? C. But what happens? What if this one, because you can easily compute this, you say this is your vector, then maybe this is, you now say that you have a vector here, and you have what? Maybe you have another vector here, isn't it? So maybe you call it y or something like that. So this vector, you have a vector here, maybe this is d. So if you want to go to d from here, you say you do what? Y after, okay, yes, okay. Y after No, y x, isn't it? Y after x, oh? Y after x, exactly. Y after x will land you into B. While simply x, on this is on A, of course, A. X on A will land you onto C, just like also what? If this is y, this is also y. So if you want to come here, what do you do from here? You want to do what? So you say what? Y inverse A is B, and so on and so forth. So you can complete this. But you have all this because you are sure you can determine the position which these things move. What happens if they don't move straight? What happens if they move like this? What happens if this, instead of straight line, decides to go like this? Later on, because there are different possibilities. Consider, for example, a bird that is flying from here. It's not natural. Maybe it will breathe it here before it reaches there, because it has freedom to move. But in our assumption, we always assume straight lines. We say you have to follow. So that's one of the disadvantages of the manifold philosophy, is it how we capture most of real life situation. We always assume perfection, that if a position has to be here, this position has to be there. So we are a bit rigid and too speculative. But if you don't do that, again, you are not going to prove your transition, because you have no idea what to do to this zigzag thing to make sure yes. So that is one of the disadvantage in physics. That's why we always are not too sure. Under best conditions, mostly under best condition, we expect it to be here. For example, you are tracking a moving object and it has left this place. So you are saying under best condition, by 7 o'clock it should be in position. So, because you are assuming straight lines and your computation have to be 1-to-1 and 1-to-1, and you are using vectors. But what happens, it may even be inside a river, so you are not always very perfect. So that's one of the disadvantages here. For example, you may wish to consider also this formula to prove this. Under this condition, let me give you this chart here. Maybe you have you start from R. To some position, maybe L or M. Okay. Then on this you apply. So you apply some mapping, maybe theta. Okay, and then when you are at U, you apply some mapping, maybe T, and you are at some position here. Okay, which you call T of U. Position here is called T of U. T of M. T of M. And you have a mapping here also. Maybe these arrows. So this is T after psi. This is T after psi. And you're there. Okay. You may also wish to come this way. That's another possibility. To some position under this, or maybe you now have a position here, maybe gamma. So So this is going to be to some point. Okay. This is going to be, this is psi, okay. This is psi, this is theta. So this position is going to be after. I think I should not put this. Maybe x. Let me call this x. This one will be x after that. Yes. So now supposing you have this, and so you now say, therefore, based on this, you say the t after phi is going to be equal to t after x inverse. After x inverse, after s after phi. And this will now be t. So if you look at this philosophy, what we are assuming is that there are perfect vectors here, and this direction here is here, sorry. From R, you apply psi to M. From M, you apply mapping T to T of M, then. Okay? From R, you can also apply, because from, if this is T, this is going to be what? If this is T here, what of this? I should have changed this form. If this is T, this is going to be Tm. Okay? This is going to be Tm. Okay? So, in that case, you are now having, so this is going to be T from here to this place is going to, this is T inverse 4, and this is psi. So this is going to be psi after, sorry, I'll change this. It's going to be psi after T inverse 4. It's going to be psi after T inverse to this position. So, and this again is going to be what? So I will change this to that one, then maybe T inverse there. I think that one is. So what of this? This is already T-O. So if you are now moving from R to T of M, it's like you are now having what? Psi. You move through psi, then through what? T, isn't it? So T after psi. T after psi. It will take you to. But this one, if you now use this, the other, you now incorporate the other side. It's like this is psi after T inverse first, then after T inverse, psi after T inverse, after T inverse, after what? T. So psi after, so I'll change this. because this portion is psi. This is psi, this is tipo. We say psi T inverse, yes. So this is psi after T inverse. So we say psi after T inverse. Psi after T inverse will take you here. And from here, if you want to reach this place, you'll say after what? After T inverse, after T. After T inverse. Okay. Yes. So when you consider, you look at after from here, if you apply T inverse, you are here. If you apply T, you are here. So you find out that, but this place is from M, from here, if you want to move to T, it is simply what? You now write T in terms of psi and T, so that means T will now be what? T after psi, after psi inverse. So if you want to write T, T will look like, why is T? T is, this T here is psi after, this T is going to be T after what? Psi after T inverse, go? Psi after this is okay. This one is actually T after psi. T after psi. After, I say I better write it like this. Psi T after psi. After psi inverse. So you want the position to look like this, so that it will combine with this to have this. Now, if you look carefully at this T, you will have so if you put that on here, you will have what? So you have this one will be T inverse after T. I use associative law, so you have an T here. Then you have what? After what? After psi. After psi. So you found out that you are going to have an identity here, because this one will give you identity map. This will give you what? Identity map. And if you have identity map, you are where you are, and so you assume that because you are going to get identity, it's like you have come back to where you have started. Okay? Yes. We'll look at it again. Let us look at it. This is psi. This is T. This is psi after T after psi. This one is okay. Because this is psi. Because this is T, we call this T inverse. Went like this. So when we have psi, we have T inverse. We will now call this psi after T inverse. This is also okay for us, isn't it? This is already T, so we have no problem. So if we move from R, we follow this. We have two ways. We either follow from this to this, and this will be what? Psi after T. That's moving from here. Or we may decide to follow like this, then like this. Then in that case we say psi after T inverse. after T now, because we are moving this way, isn't it? After T, isn't it? Then psi after T inverse is this, coming this way. After T will come this way, and then it will give you what? It will give you psi. This one will give you what? Just psi, because you need to have the two to create one. You have to have clockwise motion and basis, and so this will give you psi. Then all this after again what? Psi. So you may wish to do like this, then like this. But you know you can use associative law, and when you do that, you say this is psi after T inverse after T. So you do like this using associative law. Then after what? After this T inverse, oh? Yes. Psi after T inverse. And so this will give you just psi. After, so, did I say T? Psi after T inverse like this, go. Then we'll say after T, go. After T. After T, actually that's what. Psi after T inverse. After T, you are here. Then after T, not psi, sorry. After T. You look at psi after T inverse, you are here.
Yes.
After T, because you are getting the psi after T inverse, after T, you are here now. Then you apply what? T. Then after T, so you are here. This is what you have. So what we do, we call this, we now look at, if you look at this, this is going to give you psi after identity map. This is identity. Then after T. So this will now just give you psi after T. The same way you had it here. So it means therefore that you can either move from here to here or move down to here. You are going to have the same. And of course, the assumption of continuity that so that way you can manipulate this. So actually this is a mistake. We should not get identity, because identity, I was afraid, it's not a good thing to get, because it means we have not moved anywhere. But this one has proved that our trajectories are okay. We can use with respect to continuity, we can always move from one point, from R, we can always reach M through different routes. One is this way, the other one is this way, and we are assuming, so what we are assuming is that whether you move like this, or you move like this, you are always going to the same place. Ridiculous. That's what we have tried to prove. Up to continuity, of course. Yes, but up to differentiability is something else, because we are not sure these maps are differentiable everywhere. Isn't it? Yes, but we are sure that they are continuous. Yes. So up to continuity, you can prove the manifold philosophy of a moving trajectory from one point to another. And this also, I think this also is a good sense of, give you a good sense of transition maps. You may think of this one as one transition, this one second transition, and you are trying to see how the two are related. All right. And I think we are going to another topic now. to another. But in loop theory, you are going to take from one point, go, and come back to the same point. It's also another very important concept in topology. We shall see later. But here we are going to, and it's very also related to what we are going to talk about now, what is called homotopy. Now, in the definition of homotopy, you assume you have two spaces, maybe X and Y, and the F and the G. So, by homotopy, you remember a mapping. This is a mapping from X to Y. Okay. So such that F relates to some G, okay, let me say equivalently, because homotopy are like equivalent maps, so, and such that, so that H of X at 0 is called f of X, H at X1 is called G of X. And you now seek to what we do, we seek to investigate relationship F to G. How is F? So we write normally we say homotopy. We say F is homotopy. We write it like this times. We seek to represent to see what is the relationship between F and G. And one that relationship which defines H is a homotopy like this of X and 0 is also here. Homotopy then it means it's a mapping from actually 0, 1. Okay. X is mapped from 0, 1, so it's like you have X and you map it from 0, 1 interval and you go under H to 1 such that this definition, okay, as this definition of this one, H under X0, the same H here, under X0, will give you f of X. The same H under X1 will give you G of X. So you have two spaces, two topological spaces, X under Y. You wish to transform a mapping X is a map. Let me even say times, where it is map on this 0, 1. It takes entries from 0, 1, interval 0, 1, and then it is transformed by H within the interval 0, 1 to Y. Y is also a topological space, such that this homotopy map H, so you assume you have some homotopy map here then acting on this, okay? That's why we put it here. It's like if we don't put it here, we can put it here. Okay, h at x0 as the initial will give you f of x. The same h at x1, the terminal, will give you 1. So you assume, you imagine you have maybe a unit square. This is 0, this is 1. And remember, this is your x-axis, this is your y-axis. So you imagine maps, F's maps going from here, F1, F2, and then here you call it G. From here you say f of x, f1 of x, f2 of x. But when you reach 1, you say g of x. Okay. So now it's like we are trying to bring the two to compute the mass within that interval. And when you do that, you say you have a homotopy. So you say G is homotopic to F. Like G is equivalent as a map to X. The two maps are equivalent, like they are the same. Because they are all maps on a unit square. These are the Fi's, Fi, Fj, Fk. Well, this is G. Okay? So anywhere between 0 and 1 is F. But up when you are at 1, you say your mapping is what? Now, you have a situation like this, where it is x under g to y. Okay. So it means if this is x, if this is space x, if you apply this is a homotopy, it will take you to what? Space 1. Is it clear? You start from space x, you apply homotopy on maps, and you go to space y. So zoom, you have two spaces here. This is y, this is yes. You apply homotopy to some points here, and you have the replica. Okay? Maybe this is F1, 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 on this F, F2, F2. But when you are here, you get G, and you are now transforming. By the time you reach there, we say you have transformed from X to Y. Okay? Yes. So this is what we call homotopy of maps between two topological spaces, X and Y. We have this idea, we nurture this idea because sometimes we may wish to, we are not too sure that the maps which happen on two different spaces are the same. But what we do is that if we find them to be a bit homotopic, we assume that they are the same. Okay, they are not actually the same, but when they are we say they are homotopic. It's like we are saying they are equal, they are the same, and then they transform from X to Y. So we have that, and I think I have a lemma here in respect of the homotopy to show this lemma is also a further proof that homotopy means equivalent, because what this lemma is saying is that homotopy is an equivalent relation. That means if X is homotopic to Y, then it's like they are the same.
So, we seek to, I didn't get what we seek to investigate, okay, relationship F to G in F and G. seem to ask ourselves, what is the relationship between these maps, the F map and the G map? That's what to try to do. Alhamdulillah. Okay. So this lemma says homotopy is an equivalence Okay. Homotopy is an equivalent relation. Now, in the proof, we try to show the three properties. We try to show that homotopy expresses the three properties of reflexive, symmetric, and transitive. We use definition. S is homotopic to itself by definition. F is homotopic. Okay. Isn't it? Since now h of xt is actually okay. Or some t in you pick some t in the interval 0, 1, then you can conveniently define h of xt to be f of x. Its meaning was that x is actually homotopy to itself. Yes. So this is reflexive. Reflexive. You can choose a convenient t such that and from 0 to 1 such that h of xt is f of x. That means f is homotopy. So this is reflexive property. This is an analytic way of showing it. Right? You can also show it using the diagrams. You can, like I said, if you have the unit square with x here and y, suppose this is x and y. We are transition from x to y, and all the f's. You discover that all the f's here are f of x, isn't it? Yeah. Yes, so that means it's homotopy. Not until you reach 1, you are not going to get g of x. So for all these f's, you are going to have f of x constant for the whole region, not just 0, but all the regions between. Only at 1 you get what? G of x. Good. Now that, so to show the symmetry, the next one is to show the symmetry. We now note that again. Now, F homotopic to G, okay, by definition, since since we have by definition h of what? X0 is what? F of x, h of x1 is g of x. So we say this is f is homomorphic. But if we change this, instead of saying x, if we say h of xt, where t is where t is when t is 1, t is x minus 1, what happens? When x is 0. You know, this is h of xt here. So t assuming values from 0 to 1. Okay? So if t is 1 minus t, sorry. We have x and 1 minus t. Or h of st where t is 1 minus x. Okay? 1 minus x. 1 minus x. Not x minus 1. Then we graduate this into now when we have the 2. So h of x, when x is 0, what happens? At 0 we have what? H of x1, isn't it? Then h of x1 will be what? F of x. And when x is 1, we have h is what? H of x0. This will be x. Now if you compare this with this, okay? What happens? X at 0, x at 1. So you find out as the reverse of this is the reverse of this. So while you say this one means this one implies f is homomorphic to g, this one should imply what? G is homomorphic. Because it's opposite. Isn't it? No, h of x1, no, h of x1 is actually g of x4. H of x0 is did I say that? H of x0 because 0 means this one you put 1. So this will be the first one, H of x1. H of x1. So you start with, I think I'm correct. It's h of x1 by this definition is g of x. So you start with g of x. H of x0, sorry, I will call this x0. So it's g of x. Sorry, g of x. And I'll call this h of x1 when this is 0 to be what? F of x. So if you compare this, you see it as a reverse. This one x0, x0, f of x, but this is g of x. x1, x1, this is f of x. So that means this implies that g is homomorphic to x. And this is analytically. Why are we having this
scenario because we say 1 minus x. 1 minus t is our. So when t is 0, what it means, sir? What it means by 1 t is 0? It means x is 1. Yes, so that's why. And 1 t is 1, it means x is what? 0. Yes. So that's why you have the reverse of this. So it's like, this is analytic. So it's like now, instead of having moving from here, just like you have 0 here, 1 in your unit square. This is x, this is y. So you are now saying that you are moving from 1 to 0. So you are moving this direction now. You used to move from 0 to what? To 1. You are now moving from 1 because when you, the one up to 1 is 0 means g of x. So g of x is down, f of x is up, isn't it? So this is g of x here, f of x. Instead of f of x here. So but you are covering the same, you find out they are covering the same unit square. And you are moving from f to g, g to f. They are the same form. So there is symmetry in that sense. Because what symmetry always try to establish is that when you reverse the map, you are not going to add anything. You are still within that range. Just like you have in the parabola. In your parabola, when you have a perfect parabola here, you say this place is the same as. Well, this is F, this is G. What you are saying is tending to G as you move from minus maybe TD to plus T. We say your F tends. Just like you can also say that G also tends to F if you move from TD, F ends up reverse order, isn't it? Within the same region, the same region. So this is an example of symmetry. Good. So the next one is to show that it is transitive. Now we'll try to show that homotopy relation is also transitive. Remember, okay, we have shown the symmetrical. Now we are trying to show transitivity. We now, for transitivity, what we do is transitivity. Assume here F is homotopic to some G, and G is homotopic maybe to some H. And then we'll try to show that F is homotopic to some H. So I'll tell you the trick we use. What we try to do in this sense, establishing transitivity, is to try to work within the same interval 0, 1, but to subdivide that interval into 2. Okay? We are having the same interval. They are all dried up. Okay, so
that means H inverse H dash of so H dash X. So what the trick we use here is to show that we can cover the same unit interval 0, 1 twice as fast as we used to do. So if you increase your speed, you are going to cover it 2 times. Is it clear? First time you are at H. The second time you are at first time you are at G, second time you are at what? H. Yes, so that's why you say F is homotopy to H. Just like you have F homotopy to G and G homotopy to H means. So analytically it means you can define H to be X and 2S boson S such that S here, not T, lies between 0 and a half. Instead of between 0 and 1, you will now put S to be between 0 and a half. Then H dash of X and 2S minus 1 will lie them between half and 1. So you can see how you have subdivided geometrically like this. You have the same unit interval code. You know, this is your x-axis, this is your y, you have unit interval 0 to 1. But you divide this into half. Isn't it? So all the f's, what you have here, between f and what? G. What you have here is between G and H. So that in between 0 and 1 you have now f. So that's what you analytically, that's what you do. You now take all the mass between F and G in half the time you used to take before. And this is very possible because since this is transition from one place to another, if you double your speed, but you can cover what you can cover in 1 minute 2 times if you double your speed. Okay? It's like from this place to town, if it is going to take you 10 minutes, if you double the speed, you can reach town in 5 minutes. So that's what you do geometrically. You divide the unit interval into 2, so equivalent to what you have, you put half. Then after this, so that from this to actually from F to H is actually 1. So that is transitivity. So that means homotopy is this implies a homotopy is an equivalence. I mean is that homotopy, since it's an equivalent relation, is going to group markings into classes, one equivalent to the other. G, F, H, L, and so on. Each one into its interval. You can see this different interval. So it's going to group them into separate intervals, like partition. Look at this. It's like partition now. The F's here are related to G, and there's partition here, and G is now related to H under this partition. So that from 0 to half, you arrive at G. Then after half, you now transit. You don't talk of F now. You talk of G to H, isn't it? So if you are dividing into 3, you are going to have 3 partition, G, H, L. If you have 4, you divide into 4. So these are going to form partitions of equivalent function, homotropic functions. Homotropics or actually, you did this more. This I have example. I have an example here. F of x is equal to x squared. G of x is equal to sin x. Then h of xc defined by 1 minus t into x squared plus t sin x. So, example, consider this example. Yes. G of x and x. Then if you say h of xc defined to be 1 minus t sin x. When t is 0, what happens? When t is 0, if you allow t to be 0, then you have what? H of x 0. It's going to be 1 times x squared sin x, and this is just x squared sin x. And this is f of x, it's a function of x. What about if t is 1 half? H of x 1 will be 1 minus 1 will be 0 into what? S squared then plus what? So the whole thing is 0, isn't it? This is going to be just what? Sin x. Okay. G of x. Because you have to differentiate from this. The f of x is x squared sin x. So this one cannot be f of x. You differentiate, you say this is what? Some g of x. So that it will be different from this. Isn't it? Yes. So h is a homotropic. You can have different, you can change this. What about cos x? Supposing f of x is, supposing f of x is s cubed. Look, it's even defined here, g of x is sin x. When your g of x is cos x. Do the same. You can define h of t, h of x equal maybe 1 minus t maybe s cube plus t and h of g of x go. Okay, well, I made a mistake. Here we say f of x is x squared. Yes. So we are getting x squared sin x. But remember, t is 0 sin okay, no, we cannot say. How about s squared g of x sin x 4 minus 0 4. This is 1 s squared sin
Plus.
Plus, yes. Plus this. X square plus. This is simply 0. So we say 1 times x square 4. So we have what? X square plus sine x. Yeah, so that we can be in tune with this. Yes. So just like you can do this 1 minus x cubed cos t equal, then you can define f of x4 to be like we used to say x cubed plus, did I say x cubed? Okay. Yeah. Let me call it cos x. Not cos x. And g of x will be what? Before we used to have g of x sine x. Let's say cos x. See what happens we do. So h of 0, h of x0 will be 1 minus 0, that is 1 times x cubed. Is it plus, Neko? Yes. Plus cos x. And we define this is x cubed plus cos x, which we define as f of x here too. And g of x1, h of x1, and 1t is 1. Then we say 1 minus 1, 0. 0 times x cubed plus cos x. So this is 0, this is just cos x, which is g of x. So you can also see that they are also homotopy. F is homotopy. And so on and so forth. You can define more and more of those functions as an illustration. Concatenation of maps, and then also look at fundamental group.